Okay, good morning, everybody. Let's get started. Before we start our lecture, we're going to talk about the second midterm. Now that you guys are all relaxed and ready for another exam, we're going to discuss when is it we're going to have the exam. So we have two choices, the favorite Monday or the favorite Wednesday.
This next week?
Yeah. How many votes for Wednesday? 3, 4, 5, 6, 7. How many votes for Monday? Good. Yeah, at least. So Monday is not going to be mad with us. How many opposition to an exam on Monday? Like I have a conflict on Monday. There's no way I can take it.
I oppose it, but I don't know.
You don't need to tell me the reason.
Okay. There's no conflict.
Any opposition to Monday?
Yes.
One opposition. Any opposition to Wednesday? You're making life difficult, my friend. Okay, so apparently, when is it going to be the exam? Wednesday. And Wednesday is going to be March the 29th. Oh. Sounds good? We'll talk about what to expect on the exam maybe on Wednesday. Or, yeah, on Wednesday we'll go over what to expect on the exam. Okay. So back to our lecture. So what we're doing is the root locus, and we said the root locus will help us understand the behavior of the system by knowing where the poles of the system are for any value of a gain in the system. We can change any parameter and see where the poles are, how the poles are moving in the S space, and that knowing how the S space poles location determine the behavior of the system will help us understand how the system is going to react to any input. Now we said there are a set of rules that we're going to go through that will help us plot the root locus from the transfer function. Make sense? So we looked at some of these rules. I mean, just to refresh, how many branches does a root locus have? The root locus will have as many branches as there are poles in the system. How does the branch start and ends? It starts at a pole and ends at a zero. Make sense? What if there are enough poles and zeros and they're equal? Then every branch is going to start at a pole, is going to end at a zero. But what if we do not have enough zeros in the system? We have 3 poles and we have 1 zero. One of the branches is going to start at a pole, end at a zero. But then we're going to have 2 branches that are going to start at the pole, but there are no zeros to end at. Where are these going to end? At infinity, at asymptotes that are going to be at infinity. And we had the equation for the asymptotes, for calculating how the asymptotes look like or behave, and where these asymptotes are going to behave. So we can calculate the angles of the asymptotes, and we can calculate also the point where these asymptotes are going to be meeting, sigma, the intercept. So in this case, we have 3 asymptotes. They're all going to meet at this point here that we calculated, -4/3. And the angles are 60, -60, and 180. Make sense? In this case, we have 4 poles. Therefore, 1 pole ended at 0. But then we still have 3 poles that have no finite zeros that they will end at. And therefore, these these poles are going to have to end at infinity, at a zero that is at infinity. And these are the angles that, these asymptotes that will guide where the root locus is going to be going at infinity. Make sense? Okay. So what we're going to be doing today, we're going to be continuing, or we're going to be finishing all the rules, and we're going to be doing examples on the plotting of the root locus. So the next rule that we're going to have is the break-in and breakaway points. And these are the points where two or more branches of the root locus intersect. So if I go back to the plot that we've done with the root locus example that we had before, if I look here, although we plotted everything here in orange, when we look at it closely, what we have here is we have a branch that might look something like this, and we have another branch that might look something like this. Is that clear? There is a branch that's starting at this pole and ending at a 0. There is a branch that's starting at this pole, the pole on the left, and going to be the 0 at infinity. Now, at this point, both of these branches are intersecting. You see that? This is what we refer to as the breakaway and break-in point. This is a breakaway point because when we're starting, when k is very small, we're starting at the pole, and then as k gets larger, as k gets larger, we're going to be moving, if we are at the pole that is at the left, we're going to be moving to the right. Eventually, this branch and this branch are going to intersect with each other. Does that make sense? So these two poles, if I draw them again here, when k is very small, I'm starting here. When k is increasing, I'm going to be moving this way, I'm going to be moving this way. Eventually, there will be a point where both of these branches are going to meet each other. And that is the intersection point that we're going to be calculating. Okay. So let's do another example to illustrate this intersection point. So let's say that we have a root locus that looks like this. Now we did not say why it looks like this, but for the time being, we're going to take it as this is how the root locus looks like. So we have two zeros and we have two poles of this system. So on the real axis, which part of the real axis are on the root locus? To the left of an odd number of poles and zeros. So therefore, this is going to be on the root locus. This is going to be on the root locus. Now this root locus is going to look something like this. Together? This is how the root locus for this system is going to look. Now who can tell me how does this system behave as we increase k?
The circle get bigger.
No. No.
Okay.
How does the system, where are the poles as we increase the value of k? When k is very small, we're starting at the poles, aren't they? The poles are going to be the open loop poles. As we increase the k, what's going to happen? I'm going to start having poles. Let's make sure that is on. As we increase the poles, as we increase k, the poles are going to start moving this way and this way. Eventually, they're going to meet here. And then as we keep increasing k, we're going to start having poles with imaginary part keep increasing k. Eventually, these both are going to meet here. Increase k. We're going to start going this way. When k goes to infinity, we're going to end up at the 0. Does that make sense? This is consistent with what we said at the beginning of the lecture. We're starting at a pole, and when k goes to infinity, we end up at the 0. Is that clear? So again, if I were to just... Go ahead.
When you move to the board, it zooms out so much that we can't see. It's perfect right now, but whenever you move to the actual board, it zooms out to the full.
It does not have the full view.
We can see you and the board right now, but when you walk over to it, it zoomed out so much that we couldn't see the board.
Now, it's zoomed?
Yes, it's full room.
Okay. I'll try to avoid going to the board as much as I can. If I go there, who's going to tell me to go back? Okay. Okay, so again, I'm going to represent what happens with the pole's location with this k. When k is very small, we are starting at these open loop poles. And then as we increase k, we're going to start moving. One pole is going to move to the right, one pole is going to move to the left. Eventually, at certain value of k, we're going to have both meeting at this point. Then we keep increasing k, and I'm representing increasing k by the font that is larger. I keep increasing k. This k is going to be bigger. This k is bigger. Increasing k, k got bigger. K got bigger. And then at this point, k is bigger. K is bigger. And then they're going to meet at this point, and then k is going to get bigger. And k is getting bigger. Does that make sense? So we're starting with k small. We're starting at these points. As we increase k, we're going around. We're going to have imaginary part. Keep increasing k. We're going to go back to the real axis. When k goes to infinity, we're going to be ending at these zeros. Together? Now we can represent this differently. We can come here and represent the relationship between k and the location of the poles like this. So in this case, I'm going to just put numeric values on these poles locations. So we have this one at -2, this one is at -1, this is at 3, and this is at 5. The zeros are at 3, 5, -1, -2 are the poles. So if I come here and plot the relationship between k and between the poles location and the zeros location, the 3 and the 5, I'm going to have a graph that looks something like this. What does this graph says? When k is 0, I am at -1 and -2. When k is larger value, I'm going to be at this location and this location. When k is increased, I'm going to be at this location. My poles are going to be at these locations. When k keep increasing, I'm going to be at this location and this location. Together? Now to be more accurate, this has to be starting all the way to the top like this. And then I keep increasing the value of k. Eventually, I'm going to have a k where I'm going to go back to the real axis. I keep increasing the value of k. As k goes to infinity, where are my poles of the closed loop system going to be? At 3 and 5. Together, what this graph means? This is a representation of what we had in the graph before it. Any questions? Clear? And again, what is the real axis on this? What is it? No, the real axis. What is the label on the real axis? It's S. But since the imaginary part, we're only interested in the real part of the real axis. What is the real part of the S? Sigma. Second, S is equal to sigma plus j omega. Isn't it? But we are only interested, like our discussion now, is about this region and this region. What is omega in this, along the highlighted lines? Omega is equal to a 0. So therefore, S equals sigma plus j omega. S is just equal to a sigma. Is that clear, everybody? Okay. So let's write down what we just said. When k is equal to 0, the root locus is at -1 and -2. As k increases, poles move closer to each other. At certain point, or a certain value of k, the branches will meet. And we're going to call that point A. So this point here, I'm going to add a point here, that is A. And let's add another point here, that is B. A and B. Then as k keep increasing, the poles are going to move to the imaginary, they're going to start having imaginary part. So the poles move to the complex plane. And then as we keep increasing k, the closed loop poles will move back to the real axis. We're going to move back to the point B that we labeled there. And then as we keep increasing k, the poles will move toward the open loop zeros. Together? Is anybody confused when I say as k continues to increase, the poles will move towards the open loop zeros? What poles are we referring to?
3 and 5.
What poles of what system we're referring to when we say the poles will move towards the open loop zeros? The closed loop. The closed loop poles are going to move towards the open loop zeros. Okay. So therefore, in this graph, we have this point here that is A, and we have this point here that is B. Now, how do we find the point A and B? What tool we use to find this point A and B? What is it?
Like the tangent one?
Close.
Derivative.
Derivative, yes, excellent. If I take the derivative, go ahead.
Are point A and B graphed to have the same k value?
No, they don't. Of course not. No, they don't even. Okay, so I'm glad you asked. I'm gonna do like this, like this. This is gonna go to a k. K is gonna keep increasing. Eventually, it's gonna be at point B. Keep increasing goes to infinity.
Okay.
Very good question. Clear? There's not enough room, but this A is going to be a certain value of K. B is a much larger value of K.
Okay. Try and say. Sorry. I'm just trying to remind you to stand the man.
Oh. The standing police.
Yeah, I didn't mean
Charge me a ticket.
Yeah.
Okay. Together? So if I want to find this point, what is the tool that we can use? The derivative. What is the derivative going to be here? 0. What is the derivative going to be here at the maximum and minimum? It's going to be equal to a 0. So therefore, in order to find these points, we have two methods. And both methods will give you the same result. So the first method is we're going to say, okay, the closed loop poles satisfy this equation, 1 plus k g of s multiplied by h of s equal to a 0. If I want to write k in terms of the poles locations, I can write this as k equal to -1 divided by g of s multiplied by h of s. Together, k satisfies this equation along the branches that we're trying to calculate the breakaway and break-in points for. Together? Now we are only interested of S when it is along the real axis. So if I want to, I can just replace S with sigma. Why do I do that? Just to signify that I'm calculating all this when S is along the real axis, along this yellow line. Along this yellow line, what is S equal to? Sigma. There is no j omega. Together? Again, you can do it, you can keep it, it's up to you. We're probably going to do it both ways, but this is just a labeling. So therefore, I can write k as -1 over g of sigma multiplied by h of sigma. And to find the breakaway and break-in points, I can just take dk by d sigma, set it equal to a 0. This will give me the breakaway and the break-in points. Together? In the previous graph, which one is the breakaway? Which one is the break-in?
The breakaway is A, and the break-in is B.
Yes, the breakaway is when we are leaving the real axis, and the break-in when we're coming back to the real axis. So the first method is to take the derivative to find this point and this point. And the second method, we can solve for the following. The summation from I equal 1 to m 1 over sigma plus zi equal to the summation from I equal 1 to n 1 over sigma plus pi, where both of these are the negative of poles and zeros. So we're going to write this equation, and then we're going to solve for sigma to find the breakaway and break-in points. Okay, we'll do an example and we'll show both methods. So let's go back and do an example. So in the first method, we explained it, makes sense. We took the derivative. It will give me when k is maximum or minimum. It has a local maximum, local minimum. That will give me the location of the breaking point. The second method, I'm going to take the open loop poles, the open loop zeros, write this summation, then solve for the value of sigma. Together? Okay. So let's do an example. So let's say we have the open loop k multiplied by g of s, h of s, equal to k multiplied by s minus 3 multiplied by s minus 5 divided by s plus 1 multiplied by s plus 2. So this is the graph that we've done. Let's say it came from a transfer function, g of s multiplied by h of s, that is given by this equation here. And we're going to find the breakaway and the break-in point. So we're going to use both methods. So using method 1, since we are doing this along the real axis, S is equal to sigma. So therefore, I can write that k multiplied by sigma minus 3 multiplied by sigma minus 5 divided by sigma plus 1 multiplied by sigma plus 2, which is going to equal to k multiplied by sigma squared minus 8 sigma plus 15 divided by sigma squared plus 3 sigma plus 2. This is equal to negative 1. Where is this coming from? From the first method. We said it satisfies the 1 plus k g of s h of s. So therefore, k multiplied by g of s h of s is equal to negative 1. So this is equal to negative 1. So then we need to write the k in terms of sigma. This is going to equal to negative 1 divided by g of sigma h of sigma, which is going to equal to negative sigma squared plus 3 sigma plus 2 divided by sigma squared minus 8 sigma plus 15. So we're just writing that equation in terms of k. So we multiply across, and we can write k as equal to this value. So then we're going to take dk by d sigma, and we're going to set it to a 0. So we're going to take the derivative of this value, which is going to equal to 11 multiplied by sigma squared minus 2 multiplied, minus 26 multiplied by sigma minus 61 divided by sigma squared minus 8 sigma plus 15 over all squared. How we take the derivative of that rational function?
The quotient rule.
Anybody?
The quotient rule.
Which is?
What I like to do is I like to take the bottom function and bring it up top and change the exponent to a negative, and I just do product rule.
Oh, so you take this to the top?
So no, like for dk, so you see how on the bottom I have sigma squared minus 8 sigma plus 15 squared. I take that.
This one?
the entire square? No.
Well, this is what we're trying to take the derivative of.
Oh, not the bottom one?
No, that's the result of the derivative.
Okay, yeah, no, just do,
Okay, so I mean the rule derivative of the numerator multiplied by the denominator minus the derivative of the denominator multiplied by the numerator divided by the denominator squared. Okay? Or you can use any rule as long as it gives you the right result. Okay, so then after we do this, we solve for sigma, and we're going to get sigma that is equal to negative 1.45 and sigma that is equal to 3.8. And these are our breakaway and breaking points. Together? So we can go back to the graph that we had. This point is going to be negative 1.45. This point here is going to be 3.8. Now the second method is we're going to take the summation of 1 over sigma plus zi equal the summation of 1 over sigma plus pi from 1 to m, 1 to n. And here, we're going to take 1 over sigma minus 3 plus 1 over sigma minus 5. And this is going to equal 1 over sigma plus 1 plus 1 over sigma plus 2. And let me just rewrite this. K multiplied by s minus 3, s minus 5, divided by s plus 1, multiplied by s plus 2. So this 3 is the 3, 5 is the 5, 1 is the 1, 2 is the 2. Remember, when I have s minus 3, what is the 0? Is a 3. But when we take it here, we take sigma minus that 0. So sigma minus a 3. Okay, so after we do that, we can simplify this equation. And we're going to get something that says 11 sigma squared minus 26 sigma minus 61 over sigma squared minus 5 sigma minus 7 sigma squared plus 29 sigma plus 30 equal to a 0. And this will give us sigma that is equal to negative 1.45 and sigma that is equal to 3.8. By sigma cube. Together? Everybody? I mean, it's easy to look at the result. It's another thing to calculate it. But nevertheless, we'll do examples where we'll do the calculations. Okay. So this is the rule for the breakaway and breaking points. And we're going to apply this rule. When is it we're going to apply this rule? Anytime we have a branch that we know has to break away. So either we have 2 zeros or we have 2 poles, and we know we have to break away from that branch.
Are they always kind of close to halfway in between?
Apparently not.
Okay.
I mean, here we just have it. They're not in the middle.
Yeah, they're close. Okay.
No, I mean, it's not. There is no rule that says it is going to be. In this case, it is because there is this symmetry.
Right.
Therefore, it is. I mean, it makes sense to be like very close to the middle. But this could have had another shape, and they would not be. Okay. Okay, the next rule is the j omega axis intersection. And this is the value of k that results in roots being on the j omega axis. And what are we going to do to find this? So what we want to do, let me explain what we're trying to do. We're trying to find where does these branches intersect with the j omega axis. So this, you're looking at me because I just reached the, trying to find this point and this point here. Together? What do you think we can use to find these points? What is it? What tool that we already have studied that might help us find the j omega intersection? Starts with route and rhymes with Hurwitz. Okay, so we're going to use the route Hurwitz table to find the j omega intersection. So as an example, if we are given the characteristic equation s cubed plus 5s squared plus 4s plus 2k equal to a 0. What is this characteristic equation? Where does it come from? How do you find the characteristic equation? And like what does it represent when we are given a closed loop system, we are given g of s, h of s. How do we get the characteristic equation? We calculate the closed loop transfer function. We take the denominator equal to a 0. That is what the characteristic equation is. Is that clear? Everybody? Now, one thing that might be confusing, and it might not be confusing, so I'm not sure if I should say it might be confusing, so now it's going to become confusing, is when we're doing this, we are doing lots of these tools apply to the open loop g of s and h of s, isn't it? Like if when we calculated the breakaway break-in points, what did we use? We used g of s and h of s. We did not even calculate the closed loop transfer function. Does that make sense? So you have to know which one to use when you're using these rules. Okay, so but for this one, we're going to be calculating the closed loop transfer function. We're going to take the denominator. We're going to set it to as 0. That will give me the characteristic equation. So if I want to find the intersection with the j omega axis, I'm going to establish the Routh-Hurwitz table. This is 1, this is 4, this is 5, this is 2k. And then I'm going to calculate the entries. 20 minus 2k divided by 5. And then I'm going to have a 0, and then this one is going to fall down. How do I find the intersection with the j omega axis? I'm going to set k, so I have a row of 0. And in this case, the system will become marginally stable. And this is going to happen when k is equal to a 0. I'm going to have a row of zeros. ROZ, row of zeros. And when I have a row of 0, what do? we know we're going to have an auxiliary equation that can be read from the line that is above it. So the auxiliary equation is going to be 5s squared plus 2 multiplied by k. Remember that? When we have a row of 0, then we know this is a factor of the polynomial. So since k is equal to a 10, this is going to equal to 5s squared plus a 20. And if I find the roots of this, is going to be s squared equal to negative 4, and therefore s is equal to plus minus j multiplied by 2. So for this system, when k is equal to 10, I'm going to have the roots that are going to be intersecting with the j omega axis. When is the system stable? What is the value of k's that will result in a stable system? Between 0 and 10. Because we're going to have the row all positive. If it is between 0 and 10, there is no sign changes. When it is 10, then we're going to be on the j omega axis. When k is greater than 10, we're going to be moving to the right half plane and the system is unstable. Together? Everybody? Okay. Okay, the next rule that we're going to have, the last rule, calm down, is the angle of departure and arrival. And let's see what this means. So let's say we have a system and I put the open loop poles and zeros, and I have a pole P3, I have a 0, Z2, I have a 0, Z1, and I have a pole here that is P2, and I have a pole here that is P1. Okay. Now what we're going to find, if I come to the location here to P1, I have a branch that is going to start at P1, isn't it? We have a branch starting at P1. So we know from what we discussed is that I'm going to have a branch here. Now this branch can be like this. It can be like this, it can be like this, it can be like this, like this, like this, like this. Make sense? We do not know what direction this branch is going to leave P1. Now what this rule is going to help us know is how does this branch leave P1? And therefore we call it angle of departure, or if it is a 0, will be angle of arrival. Make sense? Now how are we going to find out how does the branch that is leaving P1 going to look like? This is what we're going to do. We're going to come here, we're going to zoom in and make this much bigger. And I'm going to come here and say, okay, I know how this is going to depart. I'm going to take a point here, and I say this point is going to be on this branch that is leaving P1. Together? We do not know where that point is, but there is a point that is going to be on that branch. Now for that point to be on that branch, I'm going to define this angle here and call this is my departure angle, theta d. Okay. Now if this point here, I'm going to call it S0, is on the root locus, what does it have to satisfy? Have to satisfy the angle criteria. Make sense? So if this S0 is on the root locus indeed, and this is the departure angle, it has to satisfy the angle criteria. Everybody? Okay. So therefore, going back out of Zoom, we're going to take a point that is S0 very close to the pole P1. Of course, these are the open loop poles and zeros that we plotted here. Now we want to find theta departure. And we said this, since S0 is on the root locus, it has to satisfy the angle criteria. So therefore, we're going to apply the angle criteria. And what the angle criteria says, if you remember, the angles from S0 to the zeros minus the summation of the angles from S0s to the poles must be an odd multiple of 180 degrees. Agree? If this is on the root locus, if any point is on the root locus, it has to satisfy that the summation of the angles from the zeros minus the summation of the angles from the poles must equal to 180 degrees, or an odd multiple of 180 degrees. So what do I have to do? I'm going to come here and find all these angles. Now where do I have to find these angles to? I have to find the angles between S0 and all the poles and zeros, aren't we? If this S0 is on the root locus, I have to find the angle from S0 to all the poles and zeros. But how I'm going to find S0 when I do not even know where S0 is? And what we're going to do is we're going to assume we are so close to P1 that the angles to S0 is the same as the angles to P1. Does that make sense? So this is, you can think of this as exaggerated distance. In reality, this S0 is so close to P1 that the angles that all the poles and zeros make to it is no different than the angles that they make to P1. Make sense? Okay. So therefore, if S0 is very, very close to P1, and I came to P1 and I find all the angles that P1 makes with the poles and zeros. I'm going to call this psi 2. I'm going to call this psi 1. I'm going to call this phi 1. And I'm going to call this phi 2. Okay? So to P1, I know all the angles that it makes with the other zeros and poles. I'm assuming S0 is so close to P1 that really the angles are the same. There's not much difference between them. So therefore, for S0 to be on the root locus, I'm going to have to take the summation of the angles from the zeros, which are psi 1 and psi 2, subtract all the angles from the poles, which are phi 1, phi 2, and theta departure, and this must be an odd multiple of 180 degrees. Does that make sense? Everybody? So the angle of S0 to all the poles and zeros are the same as P1. But there is also the theta departure, that is the angle from the pole P1 that we're trying to find the departure from. We call this theta d. We do not know what it is. So therefore, I can solve for theta d, and theta d is going to equal to the summation of the angles from the zeros minus the summation of the angles from the poles minus 2k plus 1 multiplied by 180 degrees. Is that clear? Everybody? Everybody convinced? Okay. We can do the same thing for the angle of arrival. So this is our angle of departure. We can do angle of arrival. And the angle of arrival is going to be the summation of phi I minus the summation of psi I plus 2k plus 1 multiplied by 180 degrees. So if we so happen that we have a 0 in the imaginary plane, and I want to see how the root locus is going to arrive to it, we call this the angle of arrival. And we can calculate it using similar development. It's going to have the formula be slightly different. So we're going to have theta of arrival given by this equation. Any questions? Okay. Let's do an example. And then we'll do a full root locus plots. Okay. So as an example, we are given the system below. I'm going to calculate angle of departure. And our system is g of s equal to k multiplied by s plus 2 divided by s plus 3 multiplied by s squared plus 2s plus 2. And the roots of this quadratic equation is negative 1 plus or minus j1. And therefore, I'm going to come here and plot the open loop poles and zeros. We have a 0 at negative 3. We have a 0 at negative 2. And we have poles that are at negative 3. And we have a pole that is at negative 1 plus j1 and minus j1. Together? What do you want to calculate?
The angle of departure.
The angle of departure. Now, who can tell me how does this root locus going to look like? So apparently, this is part of the root locus, isn't it? So one pole is going to start here, is going to end here. I have two poles that have to end somewhere. Where are these going to end? As asymptotes. And since we have two asymptotes, they're going to be 90 degrees. So this is going to go to a 90. This is going to go to a 90. Isn't it? But what I want to know is how does this go to the asymptote? So I want to know this is going to be departing like this, going to the asymptotes, I want to find this angle here. What is this angle? The theta departure. Okay. So theta departure is going to equal the summation of psi from zeros minus the summation of phi from poles minus 2k plus 1 multiplied by 180 degrees. And therefore, I'm going to come to this graph. I'm going to label all the angles that we have here. Okay, I'm going to label the angle and label it, and you guys are going to tell me the value of it. What is this angle equal to? You have to wait till you see that square.
Yes.
Okay, what is this angle equal to? 45? Excellent. What is this angle equal to? Close. Remember, this is 1, this is 1, and this distance is, this is at negative 3.
It's a triangle.
Yeah. Seen something similar in your previous life? Okay. So therefore, my angle of departure is going to be the angles from the zeros, which is 45 degrees, minus the angle from the poles, which is 90 degrees, minus 26 degrees, and I can add or subtract a 180 degrees, and this is going to give me an angle that is equal to 109. Together? Everybody? So therefore, this angle is slightly greater than 90 degrees, and we know this is going to keep going, and this is symmetry, so this is going to go also like this. Questions?
Why is the 180 added?
What is it?
Why is the 180 added?
Looking.
Why is the 180 added and not subtracted?
Oh, because it's in the formula. It's minus k plus 1 multiplied by 180 degrees. Does that make sense? The formula for the angle of departure, it has a 2k plus 1 multiplied by 180 degrees. So I could add 180, subtract 180, does not matter. It give me the same angle. K can be 0, 1, 2, 3, 4, 5. It will give you, like you just try to find the angle. So either you're going to get 109 or the 360 minus the 109, the same angle. Make sense, everybody? Okay. So, any questions? Other questions? Let me ask you a question. Okay, let's start doing plotting the root locus. So we are given, and tomorrow our lab is also plotting the root locus, and I'm very happy that we finished the root locus, so hopefully tomorrow you'll be able to do the lab and understand what we are plotting. Okay, so we have a system. G of S is equal to 1 over S multiplied by S plus 4 squared plus K plus 16. So again, the 180 that we added to the poles and do the formula for the departure and arrival angle comes from the angle criteria. The summation of the angle has to be an odd multiple of 180 degrees. Together? Everybody? Remember? Okay. So we want to plot this root locus. What is the first step? Plot the axis. Okay. What is the first step when we plot the root locus? The second step. Label the axis. Third step. Okay, let's start from the back. The 50th step. We're going to plot the open loop poles and zeros. So looking at this system, what are the open loop poles and zeros? Where are the poles? We have a pole at the origin. And the second pole, the roots of this is -4 plus or minus J4. 1, 2, 3, and 4. 1, 2, 3, and 4. 1, 2, 3, and 4. So we have a pole here. And we have a pole here. Good? How many branches the root locus is going to have? 3. Okay. On the real axis, which part of the real axis is on the root locus?
The origin.
Starting at, to the left of an odd number of poles and zeros. There is only one, so therefore, to the left of an odd number, it's going to be like this. Good? Okay. How many asymptotes we going to have? 2? 3. This so happened that this is going to end at infinity, but this is an asymptote. Number of asymptotes is going to equal the number of poles, finite poles, minus number of finite zeros. We have 3 poles, no zeros, therefore number of asymptotes is going to equal to 3. Okay. What are the intercept point for the asymptotes? Sigma is going to equal to -4 plus minus or plus J4 minus 4 minus J4 plus 0 divided by 3, which is going to equal to -8 over 3. Add the poles minus the zeros divided by the number of finite poles minus number of finite zeros. Okay, so these asymptotes are going to be meeting at some point here. This is going to equal -2.6. So this point here, if I were to stretch the asymptotes, they're going to meet at that point. What are the angles of the asymptotes? since we have 3 asymptotes, the angle is going to equal to -60, -60, and 180. Together? So therefore, I can come at this point here and plot a line that makes an angle that is 60 degrees and -60 degrees, and these are going to be my asymptotes. How do asymptotes going to connect to this root locus? Any ideas? How are the asymptotes going to connect to the root locus? Which one? Well, this one is one asymptote, that's clear. But from here, what is it we think, how is the root locus going to look like? We're going to depart this pole. This is a branch, and it's going to go to the asymptotes. Now, we do not know whether the asymptotes here is going to be going this way, is going to be going this way, is going to go going this way to these asymptotes. How do we find out how is it going to behave? We find the departure angle. So therefore, we're going to calculate next the departure angle. And the theta departure is going to equal the summation of the angles from the zeros minus the summation of angles from the poles minus 2k plus 1 multiplied by 180. And if I look at the angles that I have, what is this angle going to equal to? $135, because that's 45. 135. Okay, so we have the angles from the zeros. There are no zeros. So we only have angles from the poles, which is going to be negative 135. What is the second angle going to equal to? Minus 190 plus 180 degrees, which is going to equal to negative 45 degrees. Together? Everybody? So therefore, how does the branch that starts at that pole going to behave? Is going to go with negative 45 degrees and is going to go like this. Same thing here is going to go to this asymptotes. This angle here is negative 45 degrees. Together? Of course, I could have, I have it calculated, but I can also calculate the J omega intersection and find exactly where this is going to go. Okay, let's do another example. Okay, let's do one that is quick. So this one, g of s, is equal to k divided by s plus 3. So we're going to plot our axis. We're going to label the open loop poles and zeros. We have a pole at the origin, 1, 2, and 3. We have a pole at negative 3. Again, number of finite poles equal to 2, number of finite zeros equal to 0, number of infinite zeros equal to a 2. Number of asymptotes. How many asymptotes we're going to have? 2. And the intercept for the asymptotes, we're going to add the 0 minus the 3 minus 0 divided by the 2 minus 0, which is negative 1.5. Okay. And therefore, and the angles of the asymptotes, theta A is going to equal 2k plus 1 multiplied by 180 divided by 2, which is going to give me 90 degrees and 270 degrees. So therefore, I should have probably plotted the real axis. So this part of the real axis. What is it we expect is going to happen? It's going to break and it's going to go as asymptotes. Now what I want to calculate the breakaway point. So the breakaway point we have k multiplied by g of s h of s equal to k divided by s multiplied by s plus 3, which is equal to negative 1. Therefore, I can also, if I choose to, replace s with sigma. So I have k divided by sigma multiplied by sigma plus 3 equal to negative 1. Therefore, k is equal to negative sigma multiplied by sigma plus 3, which is negative sigma squared minus the 3 sigma. And to find the breakaway point, we take dk by d sigma, we set it to a 0, which is going to equal to negative 2 sigma minus the 3, and therefore sigma is going to equal to negative 1.5. Together? This is straightforward because we don't have any zeros, so the derivative was easy. Okay, so therefore, at negative 1.5, we're going to have a branch that's going to go like this. And a branch that's going to go like this. Is that clear? Where are the closed loop poles for different values of k? When k is very small, I'm going to be operating here and here. When k gets bigger, I'm going to move here and here. When k is bigger, I'm going to move this way. When k is bigger, I'm going to be at this point. When k keep getting bigger, I'm going to go like this and like this. K bigger, I'm going to go like this, I'm going to go like this. The closed loop going to start here as we increase k, and then it's going to go all the way. Any questions? Okay, we did not finish all the examples. We'll finish them on Wednesday, and we'll start the next topic, which is the design of a controller using root locus. Thank you, everybody.